So what we are focusing today is why do we need some of these combinations? Yeah, some of the things you might be knowing, but then there are certain things which you need to fundamentally understand for your better ability to take certain discretionary decisions. Yeah. So load combinations are many, and some of you might not be knowing, some of you maybe from other disciplines or other verticals like construction and all that. So let me just quickly tell you where we get these combinations and how we have to go about that. So I will share my screen right now. So I hope you can see my screen, right? So if you are not able to hear or see my screen, you can pick up your phone, you can pick up your mic and then give me a comment that you are not able to see. All right. So load combinations, its significance, that's what we are going to focus. All right. So this is what we are going to focus today. So for those who are completely new to all these load calculations, let me tell you that the load combinations are coming from this particular code and this particular clause. So clause 8.1 in IS 875 part 5 is the basis of load combinations. Yep. So you will find some of this in IS 456 also, but the basic code from which the combinations are coming is clause 8.1 IS 875 part 5. So I have kept a clipping of that code here, that clause here, you can see that. So this is that particular combination coming from. So you have a combination which is dead load alone. You have a combination dead load plus live load. You have a combination dead load plus wind load, dead load plus earthquake. This you can ignore at the moment because it's a temperature load. That is a special load combination which we will not be discussing today. You have dead load plus live load plus wind load, and then you have dead load plus live load plus earthquake. So these are the basic fundamental load combinations in a project that you have to use. Yep. Now, here there is a mention, it should also be recognized in load combinations that the simultaneous occurrence of wind and earthquake and imposed load and snow load is not likely. So there is no need that you need to combine dead load, live load, wind, and earthquake. So these two together is not needed is what that clause is saying. So that is why we are seeing dead load plus live load, dead load plus wind load, dead load plus earthquake. You don't see dead load plus earthquake plus wind. Yeah, that's because these two criticalities are not going to come at the same time as our consideration because code tells you to do that. Probability point of view, it is not possible for two natural things to occur simultaneously. So here you have dead load, live load, wind load, and then you have dead load, live load, and earthquake. Now, when you say dead load plus wind load, it includes dead load plus wind load X, dead load plus minus wind load X, dead load plus wind load Y, dead load minus wind load Y. So it includes all these combinations. Code just tells you dead load plus wind load, but that means 4 number of or 5 number of combinations. Dead load plus wind load means 4 combination: wind X, wind minus X, wind Y, minus Y. Yeah, it only means that plus X means this, minus X means it's coming from the other side. Y means in the perpendicular direction. Yeah, so these are the combinations. Now, if you expand this, you get so many number of combinations. I will come to that in a while. Before coming to that, let me tell you what are the factor of safeties that you need to adopt. So if you go to table 18 in IS 456, this is IS 456, table 18. Yep. So if you see here, you can see that dead load plus live load. Your factor of safety is dead load into 1.5, live load multiplied by 1.5. Yeah. So same way, when you are combining dead load and wind load, you get 1.5 dead load, 1.5 wind load. So finally, I'm not going to elaborately explain you this because I'm supposing that most of you know this. And finally, what you will end up is you will end up with 26 combinations like this. So if you want a list of the 26 combinations at the end of the webinar, I will be emailing you this if you need that. So you can email me in case if you want that. So 1.5 dead load, 1.5 dead load plus 1.5 live load. Then you have the 1.2. When you combine all the three, then your factor of safety is 1.2, 1.2. So you have another 4 here. Then when you combine only dead and wind, you have another 4. Then you have another 4 because the code asks you to do that. Here it is mentioned 0.9 or 1.5. So our focus today is basically on this. I will come back to that. Now again, wind is replaced by earthquake. Here also you have earthquake. Here also you have earthquake. So you will end up with 26 factored load combinations. Now, if you look at the code again, you can see here limit state of collapse. And here you can see a combination set called limit state of serviceability. Now, many of you might know, some of you might not know. So let me tell you that the factored combinations which I have listed here, the 26 numbers, this needs to be used whenever you are designing for strength. So if you are trying to ensure strength of a member, it could be designing for moments, it could be designing for shear force, it could be designing for punching, then you are supposed to take these 26 combinations. Clear? Now, if you are checking serviceability, now what do you mean by serviceability? The usability of the building. What comes under serviceability? All your deflections, your sway, your drift. So anything related to your serviceability aspects, which is not really creating a immediate failure, a concern in terms of failure, code suggests that you can use unfactored combinations. So you don't need, why do we need a factor of safety? Factor of safety is to ensure in case of an accidental increase in load, your structure doesn't come down. So that's more of a strength issue. It's not a serviceability issue. If your building vibrates a bit more than usual and then people feel uncomfortable, that is not a big problem. It's a problem, but then that's why we are considering it for unfactored load. We are ensuring, yeah, wind load, earthquake load, all these are highly considered, and then we are ensuring it, but then we are not factoring it because when you check deflection, even when earthquake or wind occurs and when the building laterally sways, we are not considering a factor of safety there because already we are considering a huge amount of load, and it's a not a threat to the collapse of the building. The deflections only creates a kind of what do you call, a kind of uncomfortability and also maybe minor cracks and things like that. So for serviceability check, we don't need to factor the load. So that's, and if we factor, why can't we factor that? Some people might have that question. The thing is, if you factor that to meet the requirement, your member sizes will be very high. So to keep your building rigid for a factored load to ensure it doesn't deflect, then it makes the structure really really large and your economy will go for a toss. So that's why we have two set of combinations here, factored and unfactored. Now, one more point, many engineers, even experienced, do not appreciate it really well. For foundation sizing, say if you have pinned your joint, you can pin or fix. That's a different thing altogether. We are not going to discuss that today. So when you pin your column, you will have a vertical reaction, vertical load on your column, which needs to be taken care of. So you provide a footing there, and load by SBC is going to give you the area required for the footing. In case if you have pinned, if you have fixed, you have to take care of the moments as well. That we will see in a different webinar. So here, this load on the column is unfactored. Yeah, so that is a unfactored load. So anyone who knows that why it is unfactored load, anyone here who can tell me that? Those who know why that is a unfactored load can unmute your mic and then just mention why is this load unfactored. Do you agree that it's an unfactored load that you need to take to find the area of the foundation? Anyone? No. Anyone?
Yes, sir.
Anyone knows why this load by SBC
Yes,
here
yes.
we use unfactored? Why don't we use a
Hello.
factored? Hello.
Yeah, good morning, sir.
Yeah, good morning.
Sir, as of my experience, why we are taking a footings as unfactored loads,
Huh.
while we are calculating the SBC,
Yeah.
we took already the say bearing capacity and factor load.
Yep.
SBC was taken by the factor load. So
Yep.
that's why, again, if we take a foundation also, we take a factor load, then it will get increasing.
Yep.
So that's why we didn't prefer the foundations are with the factor loads.
Yep. Who is this? What's your name?
Yeah, Srinivas Reddy.
Okay, Srinivas. Had you taken our free course on stability?
Yes, sir. Yes, sir. I took that free course.
Okay.
Sir. Yes,
All right.
you actually wonderful. You did everything with clearly mentioned there, and everything with clear explanation. And I really enjoyed that course.
All
Thank
right.
you so much for a wonderful course.
Yeah, thank you so much for your comments. Yeah, so here what he was trying to say is, see, when you say SBC, when you get SBC from a soil
You are
consultant,
also.
can you please mute Srinivas?
Yeah.
Yeah.
Okay. Wait.
Yeah, thank you. Yeah, so when you say SBC and when you get SBC from your soil report, say if the SBC is mentioned as 200 kilonewton per meter square, yeah, the real SBC or the unfactored thing is 3 times more than this. So 600 divided by a factor of safety will give you the SBC. So this factor of safety often as per Indian code is 3. So you have down factored SBC by 3 times, which means that the size of the footing that you are getting is 3 times higher than actual. So you have already down factored your SBC, means you are getting a larger size. So the code is not asking you to factor the load as well, because there will be a bit of higher size coming there, uneconomic coming there. You have already taken care of that. So you are not required to use a factored load here. But once you get the size and then when you start designing, yes, you will have to use factored loads when it comes to design for shear force, moments, punching and all that in your column. You are required to take factored loads. Only during sizing you can take unfactored load. Yep. So coming back to our point, so I hope you're clear with two things. That is, you have a factored combination, you have an unfactored combination, and why do we need that? Yeah. Now coming back to our point of interest. Now my question is, here you have a combination 1.5 dead load plus 1.5 index. I will mark here this combination. At the same time, you also have 0.9 DL plus 1.5 Windex. So I'll write it here. One is 1.5 DL plus 1.5 Windex. Another one is 0.9 DL plus 1.5 Windex. Now, why do you need this combination? Because 1.5 is more than 0.9. And here you have already 1.5. Here also it is 1.5. So why do you need this particular combination? When 1.5 DL is more than 0.9 DL, what is the need of this combination? So I had posted this query in LinkedIn a week back, and many had responded to that. There were some right answers in that, but then I'm not sure how many of you are following me on LinkedIn. Whatever it is, if you know the answer, again, like Srinivas did, if anyone knows, if anyone can answer me on this, please pick up your mic and then you can mention that. Why do we need? Did you get my question? I hope you understood the question. The thing is, here you have 1.5, here you have 0.9. So 1.5 is more than 0.9. So why do we need this particular combination? Why can't we throw that? Why is code asking you to do that? So who can tell me that? If anyone can attempt the answer, please pick up your mic and then answer that. It's okay if you are wrong. If you think you are right, you can answer me. Anyone?
For uplift condition,
Who is this?
Akash.
Who is that?
Akash.
Okay, Akash. Can you elaborate that?
Like we are already having 1.5 dead load, so that dead load would not be allowing this 1.5 wind to give result in uplift condition. So if we have to check any structure for uplift condition, we need to reduce the dead load by a significant amount, so we can get a better factor of safety. So if we take higher the dead load with higher wind load, that's not going to be more critical. What would be critical? Relatively lesser dead load and higher wind load.
All right. Yeah, you're right. So for everyone's benefit, let me just explain it more clearly.
Sure, sir.
Yep. Yeah. So let me just sketch one particular frame. Yeah. And assume that you have some dead load and live load in that. Yeah. And say this dead load gave me a downward load of 1,000. Yep. Now you will have, say, wind or earthquake or whatever lateral load. Yeah. So I'll consider this to be a earthquake load in that direction. So you are likely to get an uplift here and a downward force here because it's a couple in this direction. Yep. So when you have something pushing up, you can assume a desk or a bench, you are pushing it. What happens? Along the width, if you are pushing that, one side will lift up and the other side will be compressed. So that's what's happening in this particular case. You have an uplift here and you have a downward compression or a downward reaction on this particular side. So this is what earthquake or wind is going to do to your building. Now, as he rightly said, your dead load and live load is actually going to help you to resist this uplift. So assume that in this particular case, you got a reaction of say 1,100. Sorry, let me just correct that. Say, let us assume that you got a reaction of 800 and you got a reaction of 800. So when you add these two combinations, what is your final result? You have 200 on this column and you have 1,800 on this particular column because you are adding these two combinations, dead load plus live load plus earthquake. Let us forget the factor of safety for the time being. So you have 1,800 on the right hand side and 1,000 minus 800, 200 on this side. Yeah. So this needs to be designed for 200 and this needs to be designed for 1800. Everything looks fine to us. But the thing is, what do you mean by dead load? Now we made a slight mistake. Let us not take this live load here. Let us take only dead load. Yeah, because this combination is mattering only for dead load and the lateral load. So what do you mean by dead load? Dead load means your self weight of the slab, self weight of every member, then self weight of your screed, your tiles, your brick, your plastering, everything which is permanently going into the building is a dead load. Now, in your design, say the architect told you and the client also told you that your floor is 100 or 150 thickness, and then on top of it, you are going to put 100 millimeter thickness of screed, and say you are going to put granite on top of that. This is what the need of the architect and the client was. Yeah, and you considered the thickness as 100, and you also considered the granite weight, everything, and then designed your structure, and you got 200 and 1800 for your building. Now tomorrow the client took a decision that he's not going to go with any finish. He's going to have a raw finish. He's not putting any tiles right now. Or it could also be that during construction, earthquake came. That we will see later. Say the client took a decision that he will reduce the thickness of the screed, or he will not even have a flooring. And he also decided to remove a lot of walls. We had considered 200 thick walls in all the beams, and a lot of partition wall also we had considered. And the client took a decision that, okay, I will convert this into a plain building without any walls. So he's not doing any walls in the building. Now he will think that, okay, load is reducing, so why should I inform the structural engineer? And in many cases he will not. And many times a reduction in load is always considered to be really good, yeah, for a layman. So what happens? What really happens there is you don't have 1000 there, yeah, because the client, without telling you, has reduced the load. So it will say became 700, yeah, that this also became 700, yeah. So what happens now? Here this is 800, so this is not going to be 200. You are going to have an uplift on this particular location, and that is instability. You can have a overturning, yeah. So to cater to this, to account for this, to ensure that this doesn't happen, code is forcefully ensuring that by introducing a possible reduction in dead load. Now you can ask me, why then 0.9? Why can't you take 0 DL? No, 0 DL doesn't come because the structure should be there at least, yeah, for it to experience your earthquake, right? So the columns, the beams, the slabs are anyway going to be there. And you have to be logical and practical. We are not trying to be safe for any drastic bad thing that we are doing. It's not like that. We are looking at a probable possible reduction in dead load, which is taken care by reducing it to 0.9. So there is a huge amount of factor of safety there, which is quite adequate to take care of this overturning. I hope you are getting my point clearly, right? I have sketched and explained this. So that's the reason for having this particular combination in your structure. Yeah, one reason. This is only one reason, one among the two reasons that I'm going to tell you. So this is one of the easiest reason. So if you look at the code, yeah, here when you have this combination mentioned, if you carefully see here, there is a notation here, one, and in bracket they have given like that. So if you read here, not one, this is not that, yeah, you have that here. So read that very carefully. It's very clearly mentioning that this value is to be considered when stability against overturning. So whatever we mentioned is already here. The only problem is that even when we do masters, we don't look at clauses in a holistic way. Even I didn't. I mean, I was a student like you years back. So even at that point in time, never ever did we did this kind of reading of the code, nor we were encouraged to do it. Yeah, so the system, the education, the way we are being trained needs to slightly change. The way we are thinking also needs to be slightly changed. So I would tell you, when you read a clause or when you read a table, always ensure you read the clause corresponding to that table. So that's rule number one. So whenever you are getting into a table, ensure that you read the clause as well. And whenever you are going to a clause, always ensure you read the table as well, because that table or the clause might have something more to tell you. Same way, always read the note and all the corresponding subnotes. So in case if you are not clear, always get back to your teacher. So that's how you need to improve yourself. So here there is a subnote here which says this value is to be considered when stability against overturning. And one more thing is stress reversal is critical. Yeah, so these combinations are going to make your stability and stress reversal critical. So what is stability criticality? We have already seen that. Yep. And what is stress reversal criticality? We are going to see now. Yeah. So anyone here who can tell me what is stress reversal and its criticality? Yeah. Some of you have 2 years experience, I guess, or 1 year, 1.5 years experience and all that. So anyone who has come across stress reversal, please, you can unmute and talk about what you know about it. No? Okay, so for explaining this, I might need etabs. How many of you know etabs well? All right. You can raise your hand. I can see that in that case. If Srinivas Reddy knows etabs quite well. Yep. So there are a few people who knows etabs well. So I'm going to take you to one model. Yep. You can see the screen, right? Can someone tell me if you are able to see my screen right now?
Yes, sir, we can.
All right, thank you. Yeah, so here I have a building. I have modeled it for around 10 floors. Yeah, the number of floors are not relevant. I'm just going to show you what is stress reversal and its significance. Now let me come again to plan. So I'm going to show you, say, grid number 5. Yep, grid number 5 bending moment diagram I'm going to show you. So for that purpose, I'm going to elevation and then going to grid number 5. Yep, and on the right hand side, I'm adding one more window. And here also I have elevation number 5. Yeah, so here in this window on the left, I'm going to take the bending moment diagram for factored dead load, live load. Yeah. All right. So on the left hand side, you have, so for clarity, I will maybe switch off the columns. Yep. So this is your bending moment diagram for dead load, live load combination. Which combination? UDCon 2 is what I had taken. So dead load into 1.5, live load multiplied by 1.5. Yep. So this is your load combination. I mean, this is your bending moment diagram for that particular load combination. Now, this will be very clear to you. This is something pattern that you are always familiar with. you have a hogging on the left support, you have a sagging at the center of the beam, then you have a hogging, and then a sagging. It's very clear, negative, positive, negative, positive, and negative. Yeah. So you need bottom steel, you need top steel at the supports, and you need bottom steel at the center of the span. Yeah. So to make it really clear, let me just sketch the pattern of the steel that might come. Yeah, for that particular beam, in case if I detail that beam, it would be something like this. You have a through reinforcement, you might have a second layer, you might have a second layer. You have a through reinforcement, you have a extra bar, you have an extra bar, you have an extra bar. This would be the standard way of detailing. Why is it so? Because you have tension here, you have tension here, you have tension here, you have tension here, you have tension here. So this will be the standard detail of your beam. If you see the bending moment diagram, it was something like this. Yep. So beyond this point, what do you call that point? Point of contraflexure. So beyond this point, you might not need much bottom reinforcement because your moment is going to the top. Your tension is changing the phase. So the tension is at the top, tension is at the top. So you need top rebar here, top rebar here, top rebar here, and bottom rebar here, bottom rebar here. That's why you see a second layer here, a second layer here, a second layer here, a second layer here, and a second layer here, because the tension is more in those zones. Yeah. At these places you might need, and at these places you might need nominal steel. We will have to see our design. There are a lot of things that needs to come into it. I'm telling a normal, very simple beam in detail. Yeah. So this is what we know as when you learn your BTech or MTech, this is what you generally see. But then let me show you one difference here. Now in the right area, in this particular bending elevation view, let me put some other combination. Yeah, so I'll go with this UDCon 20. Yeah, can you see some difference here? So what is UDCon 20? Let us go and check which is that combination first. So it was UDCon 20, and it is dead load and EQX. Yep, 1.5. Same way, 21, 1.5, 22. So 23.9, 1.5. So let me also check that 23 combination. Yeah, so here also you can see the same behavior. So there is a deviance in your bending moment diagram. Can you see that? And it's more prudent for the 0.9 Wala combination. So here, see, in dead load, live load, let us take the same level. So maybe this particular last level. So here, your dead load, live load is giving you a moment of 16, and you need a top steel here. Yep. And if you come here, the same another combination is giving you 162 moment, but that is at the bottom. Here your moment is only 127 even, or not 127, 12 even in the middle of your beam. Whereas in the middle of the beam here you have no moment, but at the support, your bottom moment is higher than what you have in the center, much, much higher. I have created load combination envelopes. Yeah, what do you mean by an envelope? Anyone who know what is a force envelope? Okay, I will just explain. Force envelope means one diagram. Say, for example, dead load, live load gave you a combination, bending moment diagram like this. This is 60, say this is 30, and this is say 40. Now another combination, we know that 26 combinations are existing, right? So the second combination gave you say something like this. This is 70, this is 20, and this is say 25. Yeah. So in the next combination gave you this as 65, this as 40, and this as 10. Now, when you design the central section, you have to take the maximum moment. So this is 40. When you design this left end, you have to take the maximum 70. And when you design the right end, you have to take the maximum 65. So like this 26 combinations are there. You have to design for the worst case. So that's our interest. Yeah. So if you go by load combinations, you will have to do this 26 times because we don't know, we will get confused. 26 times you have to write down the combination, the bending moment diagram, and then sort out the maximum value. So to facilitate this easily, you can always create an envelope of forces. Envelope means nothing but superimposing your bending moment diagram. Say, for example, instead of writing this 3 times like this, if you get one, say take one tracing sheet, I'm telling you an old method. Yeah. And first load combination bending moment diagram. Over that you superimpose the second load combination bending moment diagram. Over that you superimpose the third load combination bending moment diagram. So once you superimpose all the 26, you will get one bending moment diagram which is superimposed with all the 26 load combinations. So that we call as factored or unfactored, whatever you choose, envelope of that bending moment. You can call it envelope of any force. It can be envelope for shear force. It could be envelope for any force for that matter. So here it is an envelope of bending moment diagram. So etabs lets you create this. I'm not going to tell you how to create it. I hope most of you know that, who knows etabs. Anyone who knows how to create an envelope? Anyone here? You can unmute and say yes. So I'm supposing no one knows how to create envelope. Yeah, so that's fine. But then creating envelope can be in a different webinar, but you can create that envelope, in which case you will get all the information in one shot. So I have already created the envelope. I will just quickly tell you. It's like a load combination. I have created that. Here you can see the factored envelope. Yeah. So if you have created the envelope, you can go here and then instead of combination, you can create factored envelope. So here it is factored envelope. Now you see in one particular diagram, you are getting all the maximum and minimum. So if you see here, the beauty is that you can click here and then right click, and this will lead you to a scroller here. So you can see that at the left end, if I move my cursor to the left end, you can see maximum 162, minimum 206, minus 206. So the meaning here is your top moment is minus 206 and your bottom moment is 162. Yeah. So your bottom steel needs to be designed for 162 at the support, and your top steel should be designed for 206 at this left support. Now coming to the center, your maximum and minimum both are positive, which means you have to design your bottom steel for 30. Now here comes the difference. Your bottom steel is for 30 moment, which is quite nominal. So you might end up designing or giving 212 at the bottom or 216 at the bottom. That's all what you need. But as you go to the left, you can see that your bottom reinforcement requirement is drastically increasing. So this is due to stress reversal. Yeah. So if you don't appreciate this, if you design only for dead load, live load, your steel detail will be something like this. But now you can see that your requirement is not that. You might probably have to give as per that diagram. What you might need is something like this and an extra bar here, here, here. Yeah. So can you believe this? How many of you are familiar with this kind of detail? Anyone? See, you are needing extra bar at the support bottom. How many of you have seen such a detail? Those who are at site also, have you seen this kind of detail? No. So many times you will end up with the critical. So that's why that combination is included in your list of combinations. Yeah. So many times you can detail it out. See, many times what happens is you already have more force here also. You have more force here also. So in that case, you might give a single extra bar like that. So that's a different thing altogether. But the point to note is that there is a good chance that you can have more steel in the support in that. And you can also see in real projects, if you are doing, you can check out these kind of behavior will be more prudent for very short beams than long beams. Say the spans are less. So many times when you design only for dead load, live load, you think that, okay, if the beam is 2 meter in span, okay, you will get minimum steel, say 212 is fine. Yes, but then when there is earthquake and all that, these are tucked between two large columns or a shear wall, then your moments in those beams, short beams, will be really higher. So if you look at shear walls, the coupler beams near, say when you have a lift, yeah, see when you have a lift, you will have something like this, yeah. So this is wall, this is a wall, and then this beam, it's a very short beam. It's the lift opening, the door of the lift, and this top portion of your lift, that's like a coupler beam that might have these kind of challenging force patterns. So you will have to carefully see all that. Yeah. So that's the significance of that particular combination. So there are two things that you need to look into. One is the stability aspect, and second is the stress reversal thing. Yeah, so these are the two different reasons that code has given you so many number of load combinations. Yeah, so there are many more significances for some other combinations. Everything we cannot cover today, but I have told you two important reasons for having this particular combination in your list. Yeah. So any questions on this, you can raise now one by one. Or if you want me to talk about something else interesting for some time, if some of you are available, you can tell me. So any questions from these, you can unmute and ask me. Nothing? Anybody?
No, sir.
Okay. Is it clear to everyone? Do you want me to explain anything again? Anybody who is not really clear about how to create combinations, how to create envelope in etabs, all that you leave. Only the point, why we need these many combinations and why these two combination or this one combination is very critical. Anyone has any doubt, please raise and ask me.